this is where we left before lunch. At a summary of parametric and non-parametric clustering, and with this we are going to, with the next slide we are going to wrap up clustering vector data. And we are going to move to clustering of graph data. So let's summarize again what we know about clustering vector data in terms of comparison between parametric and non-parametric, and when each method is recommended. So pretty obviously from what I've said so far, parametric clustering is actually more efficient numerically, but it is restricted in some way to the situation when we know the shape of the cluster, so we know what kind of parametric model to use. We know that the number of clusters is not too large, which means not too many small clusters, and not too many outliers, or hardly any, preferably. For non-parametric clustering, some methods admit arbitrary cluster shapes. So all of them, all the ones based on density estimation or density level sets, admit arbitrary cluster shapes. They are very good and highly recommended if you expect many small clusters, or many outliers, or any huge variation in cluster sizes. But some of them are restricted to the case when you have small dimensions. Not all of them. You can go around. And lastly, the Dirichlet mixture models. They are somewhere in between parametric and non-parametric, in that they require you to know the cluster shapes, but they are very good at accommodating, are very flexible at accommodating cluster sizes, outliers, and arbitrary number of clusters. However, they are like non-parametric methods in that they are expensive to compute, very computationally expensive to optimize. And do require, as any non-parametric, again, like any non-parametric method, they require large amounts of data to work well. Now we are moving to the completely different chapter, something completely different from what we've done so far, which is clustering graph data. This is also known as similarity-based clustering, or pairwise clustering, or clustering of dyadic data. All of them mean the same thing. And they mean that basically instead of observing points in a vector space, we observe points in an arbitrary space. And what we observe, the things that characterize the points are not values that are associated with a single element, but with pairs. And they are typically called similarities. This data appears in many situations. Now that the paradigm is established, you only need to look around to see more and more examples of these. One of the prime examples was, and one of the early examples was in image segmentation, where this framework was developed for practical purposes. It worked well to model pixels, not so much by their intrinsic quality, but by how similar they are to nearby pixels. And that's where a lot of the initial work was developed, because it was one of the more competitive methods in finding objects in images, which is called image segmentation. But indeed, there is a lot of true network data, and some of you are actually working on it. There are social networks, there are computer networks, there are protein-protein interaction networks, just to name a few. And in a similar way, people use these models for language, text, linguistics, comparing languages between each other by their similarities, and so on. So the area is growing. What I also must say is that the area is growing in two directions. With graph data, clustering is not the only problem you want to solve. And so generally, there is a huge area, there is a very strong impetus in developing right now network analysis of all kinds. Classification, prediction on networks, predicting links, finding coordinates for the points, embedding points, and you'll see a little of that when we talk about clustering, and among others, finding clusters in data. In particular, when a network is very large, this is something that I hope, but I'm not sure I will, well, I hope to talk to as one of the last things I talk about, is the following paradigm. When a network is very, very large, maybe it doesn't make sense to cluster the whole graph. But it makes sense to start from a seed, to say, take this node. What's the cluster that's around this node? What are the nodes around the neighborhood that is actually like this node, starting from a node? But back to the standard paradigm for clustering, the data that we are given is in the form of similarities, and the similarity is summarized in a single number. Instead of many dimensions, the number is the Sij similarity between I and j, where I and j are two nodes. And we assume that the similarity is a symmetric function. So I am as similar to Sergey as he is to me. And it's non-negative, so we do not deal with dissimilarities. It's an open question how to deal with attractions and repelling forces in the same time. Okay, and the idea is that I want to group the nodes in clusters so that more similar nodes are together in the same clusters, and different clusters contain nodes that are dissimilar from each other. Because much of the data comes from network, or also because graphs are such a good vehicle for explaining concepts, very often this is cast as a graph problem, where the nodes or the points are the nodes of a graph, and the similarities are weights on the edges. And in particular, if there is no edge between two nodes, I assume that there is zero similarity. And so clustering, if we talk about the nodes of a graph, can be thought of as cutting the graph into pieces. Okay. So before we actually go into algorithms, let's think conceptually in how can we think of cutting a graph into pieces or clustering network data or similarity-based data. The simplest and more direct framework, and that I have already spelled out, is make the graph disconnected, remove edges between clusters, or remove edges of low similarity in some way, and what is left, the connected components, are the clusters. And this is the graph cuts framework. But maybe there are other ways to think of it. Let's think of the similarities expressing some local pattern of behavior, but clusters are about finding the global among the local. So we want to extract something global from the local behavior, so we'd like nodes to be grouped if they behave alike with respect to the large scale structure of the network, and not with respect to each node in particular. And that's what I mean by clustering by similar behavior. And you'll see an example, a small example soon. Or a third possibility is to basically use an already solved problem to solve this new problem, map the nodes into vectors, and then cluster the vectors. And that's called embedding. Embedding is a name for mapping into a d-dimensional real space. By the way, it is funny that one way of solving the graph clustering problem is by embedding, because here I have this formula that says that while the similarity is a single number, I can construct it by measuring different features in which nodes are similar. And a typical example is in social networks. Two people are similar if they write a paper together, but they are also similar if they attend the same classes. And they could also be considered similar if they go to lunch together, or if they email a lot, or have phone calls in between. And so there are many features that can measure similarity. A typical way in the field of combining them is to just sum them up and exponentiate to make sure that we get a positive number. In particular, sometimes these features are distances, like differences between nodes when the nodes are vectors or points in a space. So the difference between where I live and where my colleague lives can be considered a measure of dissimilarity. If I take e to the minus that distance, I get from real value data to similarity data. And that's a very often used method. So we take vectors, map their features into similarity, and then we think of going back. And this is not completely wrong, as you see. It can be useful. So enough about paradigms. Let's become a bit more precise. Assume that now our points are labeled 1, 2 to n. And the set of nodes is called V, typically the set of nodes of a graph. And instead of edges, I'm going to have the similarities Sij, which are weights on the edges. And I'm going to define the following things. First of all, the volume of a node, it's what used to be, it's also called the degree of a node. Number of, if the Sijs were 0 or 1, it would be the number of edges incoming into node I. If the edges are weighted, it's the sum of the weights of those edges. I generalize this, I extend this to volume of a cluster or of any subset of the nodes. That's why I don't call it degree, but volume. The volume of any subset is the sum of the degrees of the nodes inside, which means that it includes weights inside the set and going outside from the set. And in particular, the volume of the whole set V would be twice the sum of all the similarities. Then I'm thinking of how to cut the graph. So the cut between two sets is the sum of edges that cross between the two sets. And this is given by this definition. And now I'm going to define a more sophisticated cut, which is called the multi-way normalized cut. And in a moment, you'll see why this is necessary. So what is the multi-way normalized cut? If I have just if I break the graph into two parts, so if I break V into two parts, then this is just the cut between the two parts multiplied with with the inverse volumes of the two parts. This is also called balanced cut. And the reason this is interesting is for the following reason. I'm going to want to cut where the sum of the similarities is low. So I want to create cuts of low value, preferably 0, if I can. Yes. However, this definition says in order to the normalized cut to be small, I need to have the cut to be small, but also these volumes not to be too, but these volumes have to be large enough, as large as possible. Yes. So I can't have a single node here, because then I'll have a small cut, but it will be multiplied by a large number. That's the meaning of the balanced cut. And this definition immediately generalizes to this definition, where I can think of breaking the set V into k parts. So getting a partition, a clustering delta. And this is a definition. It's the cut between a cluster and a different cluster normalized by the volume. And it's going to be the sum of the normalized cuts of all pairs if you decompose the sum. Okay. I'm sorry, this is still didn't appear. So this is what's on the missing slide. Suppose I have a graph like this. Really strong connections here. Strong connections here. And maybe a weak connection here. And these are also weak connections. What's the minimum cut in this graph? The minimum cut in this graph breaks this edge. So if I wanted, by the way, the minimum cut is a polynomial time algorithm. It's a max flow mean cut algorithm, which is nice. However, min cut will do something that I do not like, because it will tend to cut out outliers, just like minimum spanning tree. Tends to cut out outliers. Whereas the minimum normalized cut, if I want to break the graph into two, the normalized cut will say, well, this is a cut that's slightly larger, but it leaves two clusters of large size on each side. Therefore, it does minimize the normalized cut on this graph. And it chooses this grouping, which from the user's point of view is a much more reasonable grouping. And now what you didn't see on the other slide is that with this concept, so using the normalized cut instead of the simple cut eliminates outliers from the start. It's also useful in various situations where I'm going to represent with real data, points, and where you can think of distances as being, inverse distances being the similarity. So for instance, if I have a group of points here and another group of points that are in this shape, a crown around. Well, going to similarities and looking for graph cuts tells me that no matter what the shape of this group will be coherent, this group will be coherent, in between the similarity will be low, so the normalized cut will choose to separate these two groups. And in fact, any other clusters I might put here, as long as they are well separated in space, no matter what the shape, they will be, given the correct k, they will be separated correctly by the normalized cut. Moreover, if you can see, there is an example that's even trickier. Suppose I have an area where here I have points that are extremely dense, and here I have points that are sparse but sort of regular. If you don't stretch this too much, and again, stretching changes the clustering, then the minimum normalized cut will go like approximately like this. Not exactly on the line. We'll go with a bit of noise, but we'll separate these areas too, which is somewhat counterintuitive. And when you see a better explanation of what the normalized cut is doing, you see why this is also true. So it's extremely versatile, and this is one reason why it's also used for vector data. I'll tell you later what are the cautions that you must, or how you have to be cautious about using it on vector data. But besides graph data, it can help with vector data as well. Now let's think how we might. By the way, if I give you a graph similarities and I say minimize the normalized cut, that's an NP-hard problem. Now we are going to look at the graph clustering from a fresh perspective, which will eventually get us back to the normalized cut. So we can think of a graph with weights on the edges as defining a random walk in the following very simple way. Probabilistic way. We look at the similarities. They are positive. I normalize. So Sij for fixed I defines a row of a similarity matrix. I normalize by the weight of the row, which is di. So di is the row sum in the similarity matrix. And I get something that's Pij that is a probability. Because if I fix I, it sums to 1 over j. In matrix notation, I can write it as the similarity matrix S is multiplied to the left with the inverse of the degrees. And that gives me a stochastic matrix, and the stochastic matrix is the transition matrix of a Markov chain. So any weighted graph defines a Markov chain over the nodes. And so now I can think of grouping the nodes by how the Markov chain affects them, or how the weights affect the Markov chain. And one simple idea is the following. Suppose that this is a simplified version of this example. Yeah? I have an exterior ring, an interior ring. I have strong similarities within each cluster, yellow and red being clusters. And I have weak similarities of value 1 in between the two rings. Yeah? And you can write the transition matrix, the similarity and the transition matrix of this graph. I haven't written that. I have written the following thing. If I pick one node I, what's the probability that it transitions to a yellow node, including itself? And that is 4 over 5. And the probability that it goes to a red node is, of course, 1 over 5. If I pick a red node, I have these probabilities, with 2 over 3 transitions to red and with 1 over 3 transitions to yellow. And if you think of what happens with this with the matrix P when I do these operations, I sum columns of the matrix P to get these vectors. Transitions from I to a cluster instead of transition probability from I to a point. Yeah. And what is nice in this case is that this grouping is supported by these transition probabilities, which are equal for every node in the same group. Yes. So all the yellow nodes transition in the same way, all the red nodes transition in the same way, but only when I look at the group level, yes? Because node I transitions with probability 1 over 5 to this j, but transitions with probability 0 to this other j. Yeah? And it transitions with probability 0 to this yellow node here. So if I look at individual nodes, I don't see this pattern, but if I look at, if I know what the clusters are, and that's a point that we have to address later, then there is a very nice similarity between the nodes, and I could group them by it. But I knew the clusters in advance to be able to do that. I can phrase the same thing now as an embedding. I take these values, and I call this the x coordinate, I call this the y coordinate, and now I map points in the 2D space by these values, the transition probability to red and the yellow. And well, not surprisingly, every yellow node maps here and every red node maps here. So now I could trivially cluster these data into, by any real value, by something like k-means or any clustering algorithm that you know, into 2 clusters. Okay. That's nice, but again, I already knew the clusters when I did that. So how can I get an algorithm from here? Moreover, not all graphs do that. So if I take the similarity matrix of this graph, I get this embedding. Now you see that in this embedding, it amplifies the distances between clusters, but it's still not clear how good this is for clustering. So I may try to cluster these nodes, but it's not so very good. So a question is, when do I get good embeddings from a graph and when I don't? And then another question is, in how many dimensions do I need to embed? Okay. So next comes a theorem that actually answers all these questions. First of all, a definition. I call a vector like this piecewise constant with respect to the clustering, which means that it takes the same value for every element I which is in a cluster. So I'm given a clustering and I'm giving a vector, and the vector is either piecewise constant with respect to the clustering or it's not. Of course, it's a very rare case to be piecewise constant. How rare? This is a theorem that says how. And it says the following thing, that a transition matrix P will have, if I'm given a clustering and a transition matrix P, and I compute these sums of transitions from I to a given cluster, if I manage to make them constant, which is what I get here, and these are sums inside the matrix P, then the matrix will also have, among its eigenvectors, k eigenvectors that are piecewise constant with respect to the same cluster. And now this makes this proposal much more appealing, because to do these sums, I need to know the clustering. But if I compute eigenvectors of a matrix, they are the same no matter sort of, computing the eigenvectors is independent of any clustering. And what this theorem says is that the eigenvectors of the matrix will show if there is any clustering that is perfect with respect to this transition matrix. Yeah? Yes, with some approximation. So this is a real matrix. Well, I don't show the matrix. But this comes from a real matrix with about with 40 elements. I added some noise. So there is an algorithm for creating perfect matrices that comes from the theorem there. I created a perfect matrix. I added a little bit of noise. And these are the eigenvectors 1, 2, and 3. The first one is always 1 in a stochastic matrix. So that shows nothing, ever. This is the second eigenvectors, and it's not perfectly piecewise constant, but it's almost piecewise constant. And this is the third eigenvector, and this is the mapping. Like if I project in the coordinates of vector 2 and 3, this is what I get. Very clustered data. Are there questions? Yeah.
So you're saying that I can choose any arbitrary clustering and then write the transition matrix for it and do a spectral decomposition?
No. I was saying that if there is any clustering, if I am given a P, yeah, and I'm wondering, is there any clustering for which this gives me this nice sort of a good, for which I get something like this if I do it knowing the clustering? And the theorem says if I take the eigenvectors, I'll see the clustering in the eigenvectors. Yes? So if I take the eigenvectors of the matrix, they will show me how to group the nodes so that they map nicely to 3 coordinates. And it tells me also how many coordinates I need. I need k minus 1. Yeah? And at that point, I don't need to sum the rows of the matrix. I can use the eigenvectors for clustering. Yeah?
Is this kind of like sort of taking a random walk across the graph and taking a limit?
Yes, yes, exactly. And I'm not sure I have the slide. No, I don't have it. Basically, that's why it's called lumpability, because lumpability is with respect to the random walk. If you, I don't know how many of you have looked at Markov chains in this respect, but basically, if you group the states of a Markov chain and look at transition probabilities between these sort of groups of states, you can calculate these transition probabilities, but they are not, the process is not Markov anymore. Yeah? In the sense that if you know the past, you can predict the future better, the future group of states better. Yeah? And so basically, in general, you can't group the states of a Markov chain and get a Markov chain. You get a process with memory. Yes. And this theorem corresponds to Markov chains and groupings of states that have no memory, that are Markov. So if you have a theorem like this holds, then the group Markov chain is also a Markov chain. Ask me more. I can't. This is interesting, but ask me more after the course if you want, because we need to move. Okay. And I call this the spectral mapping. This is an embedding from graph nodes to Rk minus 1. And now you probably have guessed what follows. It's the idea for a whole family of algorithms. But I'm going to describe only one, the one that's derived directly from this property of the eigenvectors. So I have, this is a graph, a social network. I get the similarities. I normalize the similarity matrix to get transition probabilities. Oh no, this is a similarity matrix. And this is the similarity matrix of this graph. You see it has a lot of zeros and a lot of small values. I normalize the rows, then I get a transition matrix. This is a transition matrix. And then I do the spectral mapping, which means I compute the first k eigenvectors, discard the first one, which is 1, and keep the others. And it's not very visible, but here I get the points. And then I can cluster them by one of the vector clustering algorithms that you've seen. Now, in text form, the same thing. I first do a preprocessing step. I compute the degrees. I normalize the rows. And I get the Markov chain. Then I compute the first eigenvectors and eigenvalues. And I embed the data in the space spanned by the vectors 2 to k. And then this algorithm says use k-means to cluster. There is a deeper reason, I can't go into it, which says that k-means is actually good, in the sense that the distortions up to some point are quadratic. So if I add noise to a matrix like this, up to some point I get quadratic, I get balls around the original eigenvectors like as perturbations. So it's natural to use k-means around the centers. Of course, as in any k-means algorithm, initialization matters. So either use the fastest first traversal initialization, and that's what I recommend primarily, always, or use something that is a fastest first traversal that looks at angles instead of distances. Yes. So that's the same as fastest first traversal, but where I find instead of choosing the furthest away possible center in terms of Euclidean distance, I choose the furthest away possible center in terms of angle. And this comes from an experimental, basically from empirical results that show that for many real matrices, perturbation, so which we always assume that a real matrix is a perturbation of a perfect matrix. That's our premise for clustering. So in many real cases, if you have perturbations around real matrices, that give you coordinates that are sort of along lines. So the norms of the points when you map them vary a lot, but their directions as vectors doesn't vary very much. And so it makes sense to look at distances in angle without looking at the norms of points. If you look at distances, you may pick an outlier which is far away from the origin. It's not completely understood why these perturbations work this way on matrices, but empirically it's a good initialization. Okay. So this is the algorithm. This is only one of many algorithms. However, most of them are variations on this theme, by and large. There are also many variations on this theme on how to compute the similarities. Sorry for the citations, by the way. They will appear soon, I promise. Coming soon. OK, so what are the advantages? I'll start with number 2. It's elegant mathematically. And that means that we can prove things about it. We know what we are doing. In particular, we know when we get clustered data and what it means. If you cluster a graph and get points, you know what it means. It means that points are similar with respect to their global behavior to other clusters in the way that I described. If we talk about points in space, then it accommodates. So if I want to do it for vectors, it accommodates arbitrary points in space. However, the caveat is that, number one, I have to have separation. It doesn't have to be perfect separation. For instance, if I have a lot of nodes here, but just a little trail of outliers here, that can be dealt with, as long as there is enough mass on both sides. That's dealt with elegantly. However, there is another caveat. Again, it's not serious, except that it requires large separation. With real valued data, you never get perfect clusterings, except when the distance is infinite. Yes? So you are always going to have some noise. So in some sense, real valued data is only artificially shoved into this framework. Then, it's actually not so bad computationally. It's pretty good. First of all, it's a one-shot algorithm. You don't iterate anything. Except that eigenvector computation is not cheap. However, it's modern algorithms. First of all, there is a lot of work in making it fast and efficient, because eigenvectors are necessary for many large matrices. So if you want software to compute eigenvectors fast, look for it, because you will find it. In particular, if you want only k instead of n eigenvectors, so think of n as large, thousands, and k small, because you are in a parametric framework, 3, 4, 10, 15, yes? If you want only a small number of eigenvectors, there is an iterative algorithm. Landsearch, or Arnold is the most more sort of generalization of Landsearch, which has this number of, this is capital K, this number of steps per iteration. So it's fairly efficient. How many iterations it takes depends on the properties of the matrix. But in particular, if you have a good clustering, and we'll talk about what a good and stable clustering means tomorrow, then that will show also in the numerical properties of the algorithm. So it will run faster if you really have a salient clustering. That's something that happens a lot in clustering. If the clustering is better, the algorithm actually works faster and better. Of course, the downside is that you need to know k. And if you don't know k and you overestimate k, then you get extra dimensions that are irrelevant. So it goes completely wrong if you don't know k. So my recommendation is that if you are not sure what k is, or k is large, try to underestimate k. Because, as you saw in a previous picture, this one, when the noise is not too large, then it's enough, a small number of eigenvectors are enough to determine all the clusters. You are going to always have k eigenvectors if the matrix is nearly perfect, but you don't need, in general, you don't need all k to determine the clusters. By the way, you can also prove that they are, they are eigenvectors, so they are linearly independent. So they are not redundant, so algebraically speaking. Okay. Another reason to remove, when you have large k, to remove some of the other eigenvectors is that noise in the matrix maps to noise in the eigenvectors in an uneven way. So the first eigenvector is always 1, has no noise. The second eigenvector has some noise. The third eigenvector has more noise, and so on. So the further down you go, the more noise you have of the noise in the matrix. So you remove noise by just truncating the dimensions. Yes?
If you do that, what properties of the graph are you throwing away?
So the question is, are you throwing away, if you remove some eigenvectors, are you missing some clusters?
Yeah, because if you have the global properties in your graph, you can be together with certain eigenvectors, and you start throwing some away. Don't you lose?
So yes, so the question is, don't I lose some clusters if I throw away some eigenvectors? Not necessarily, but I do not know of any result that will tell me. I suspect that one less eigenvector should not matter, although, so it can't be proved that you are not missing any clusters if you throw away some eigenvectors. But I don't know of any result which says that how many you need and in what conditions. Yeah.
The eigenvalues, or maybe you already said this, but do the eigenvalues give some hint as to how many good clusters you have?
Okay, so the question is, what do the eigenvalues tell me? They tell me something important. So the theorem says that you are going to have k eigenvectors among the n. It doesn't say which ones. And the algorithm says take the first k. So there is a gap. There could be clusterings that you will be missing because there are other eigenvectors than the first k. And in fact, I, with a student, developed an algorithm that looks through some number of eigenvectors and tries to find the ones that are pertinent to the clustering and throw away the others. So I would like, so basically the algorithm works when there is the extra condition that these eigenvectors are among the first k. And to be among the first k, for an eigenvector, so to have a high eigenvalue, near 1, all the other eigenvalues are below 1. So to have a high eigenvalue means that the cut actually has to be small. Yes? Again, the theorem didn't say anything about cuts. Just said if I have piecewise constant eigenvector, if I have perfect clustering, then some eigenvectors show it. If the first eigenvectors are if those eigenvectors are the first k, then it means that I have also minimized the normalized cut in the graph. So in general, if I have them among the largest eigenvalues, then I'm minimizing. So if they are the first k, I can prove that I'm minimizing the normalized cut. If they are among the first k, it means that I have a small cut between clusters. Otherwise, it just means that the nodes are the same, but not necessarily that they don't transition very much to each other. In particular, there is this kind of clustering. You can have a bipartite graph. And let's go back to a picture that I already have. This one with yellow and red. Imagine for a moment that red only connects to yellow and never to another red, and yellow at the same time. That's a bipartite graph. So you only nodes only connect to the nodes in the different class. This will also give you piecewise constant eigenvectors at different values, but also piecewise constant eigenvectors. It's very easy to verify that, yes? However, this wouldn't be a small cut. It would be the largest cut in the graph, in fact, if I did that cut. And so basically, this clustering applies also to large cuts, not to small cuts. And in particular, the eigenvalue corresponding to this piecewise constant eigenvector is -1. So it's the smallest eigenvector of the eigenvalue of the matrix. So there is information in eigenvalues, but it's more, I have left most of it outside. And tomorrow you'll see that there is information in the eigengaps as well. Important information. Yeah? So when I'm running the algorithm that I just described, which picks the first eigenvalues, it means that I'm not only trying to find nodes that are alike, but also to minimize the normalized cut. And under these conditions, I'm going to find these. And these too, unless the cut is too large. So I have to, like, this doesn't work for any values. OK, other questions? OK, some more about eigenvectors and outliers. As I said, not knowing k is a pretty serious problem here because k is the number of dimensions. So again, you can imagine algorithms where you try different k's and see what's best. But there is another problem. What happens if you have an outlier? Well, an outlier, especially in these Euclidean space settings, will actually create an eigenvector that's 0 everywhere and is very high on the outlier. So an outlier always takes a cluster, no matter what you do. Like in k means you can avoid it and so on. But if you think you have k clusters and you have an outlier, one of the k clusters will be the outlier. And this creates a problem. And in particular, any decent algorithm will look for eigenvectors that actually catch outliers and remove them, and then search for more eigenvectors to fill in the clusters. So you can remove outliers by this method, but it costs an eigenvector for every outlier. And I mean outliers that are far away. These are fine. These are dealt with very well. These are not a problem. OK. Another problem that is very serious is that the result of the clustering depends heavily on what the similarities were, what Sij was in first place. Clearly, if I take some monotonic transformation of the similarities, I can transform a perfect matrix which has piecewise constant eigenvectors into one that doesn't. So, and you can't expect somebody like a doctor or somebody to come and give you just the right similarities. So it's an art to construct similarities. And people have noticed that, and there are some references here, mysterious for now, which says that people have actually tried to learn the similarities. So in fact, get features. So we are given features. We know what is relevant to similarity, and then we learn the combination that gives us a good clustering. Of course, for this, somebody has to give you a clustering to start with. So it's learning in a supervised mode. Okay. And I want to mention only one of the variants. So I want to single out one of the variants, which is called diffusion maps. Why diffusion maps? What it does is very simple. Vk is the coordinate, is eigenvector. This method rescales the coordinates by the lambdas. Yes. So the first eigenvector number 2 will have the largest lambda. It will be scaled by lambda 2. Eigenvector number 3 will be scaled by lambda 3 to some positive power. Think of it as 1 or 2. What this does has two effects. One, the most empirical effect is that since there is more noise in the lower rank eigenvectors, by multiplying them with lambda, you decrease their importance. So you attenuate the noise. But it has also deeper meanings, because there is a reason this is called diffusion maps. it relates to the diffusion on the graph. So the diffusion is another word for the random walk. However, if you map vectors in this way, and if you use all the eigenvectors, you get actually a metric between nodes, which relates to how close they are in the sense of how many paths go between the two nodes. So a distance that's related to the random walk, to the diffusion. And you get, if you use all eigenvectors with multiply with eigenvalues, you get an embedding that where this distance is preserved. In addition, if you only use the largest eigenvalues, you get an approximation to that. This is not so important for clustering, so I can't say this is really much better, definitely much better when you want to cluster the points. However, you may want to map the points into d-dimensional space for other reasons, like to embed them, just to give them coordinates. And in that particular case, it makes geometrically more sense to use the diffusion map. So it's a more principled way. And it has other advantages. But they are not relevant necessarily for clustering, but for embedding. OK. In the last 5 minutes, another similarity-based clustering algorithm, which is completely different. However, it's different in a complementary way, whereas spectral clustering was strongly parametric because it was very dependent on k. This one is very non-parametric. It doesn't require a k at all. It requires a smoothing parameter, just like the non-parametric clustering algorithms for vectors. And this is called affinity propagation. And it's actually fairly popular. What's the idea? The idea is very similar to mean shift, or to the k-medians algorithm that I explained. Basically, we are going to choose centers. In some sense, we are staying on a graph, so the nodes are never embedded. But among the nodes, there will be some that will be called exemplars, and they are the centers of the clusters. So each cluster has one exemplar. And each node is assigned to one of them. And that's what labels it as labels its cluster. Okay. And I don't fix the number of exemplars in advance, but I fix them by way of the similarities. So here I have similarities Sij. They are the same as the capital Sij's from before. And they are given, but only for nodes that are different. So the self-similarity is a free parameter. I'm assuming that there is no such thing as self-similarity that comes from the data. And then when I set the self-similarity, if I set it high, it means that for a particular node, that means that that particular node wants to be by itself. It's very individualist. If I set the self-similarity to low, then that node will be happy to go and group with other nodes. So the smoothing parameter is one per node and is denoted by the self-similarity. And then the algorithms run by defining the two other quantities, the AIK and the RIK, yes? In addition to Sij, which are given. And AIK is called the availability. And any node, if it wants to see how important it is to other nodes, availability is like popularity. How many other people like this node to be an exemplar? And this is AIK. Support from node I to k to be an exemplar. And the responsibility is the opposite, is how good is node k to represent node I. It's not how much I likes k, but how much k is good for I. Yes? And so if you think of voting, AIK is the popularity, and RIK is the responsibility. So responsibility is how much this particular candidate reflects my views. And AIK is its chance of being elected. And the clustering basically balances these two. Okay. And now the algorithm. I start with similarities. I give a parameter lambda. This algorithm doesn't have a probabilistic meaning or a probabilistic model. And after I finish, I'll ask you what does it look like? Because it has a clear source of inspiration, but it's what it is, an inspiration. Okay, so I start by setting the popularities to 0, and then I do the following. Something that you are sort of used to by now, I update the popularities, which means assignments, and then I update the responsibilities, which means the likelihoods. Yeah? So when I update the availabilities, I look at the sum of the similarity between the node and its popularity, and how much I like it. Yeah? And I take the maximum, and then the responsibilities are taken as, so the responsibilities are taken like this. If I'm a winner, is how much I win by, and if I'm not among the winners, if k is not among the winners, no. If k is not among the winners, is how much it loses by. But if k is among the winners, is how much it wins with respect to the next best candidate. And again, there is no theoretical justification for this. I'll tell you what's the analogy. And then I have to update the availabilities by this, and the availability of every node is the sum of its responsibilities. Yeah? So here I relate the popularity by the fit of the node to represent other nodes. And then, so I can alternate between these two steps until I converge. So this again has no, it doesn't have a convergence proof, and it's not clear that it will converge in a finite number of steps. But typically it does converge after a while. And then when I'm done with the iteration, only then I can assign an exemplar by summing the responsibility and the popularity and maximizing that. So I assign every point to whomever is best for it in terms of the sum. This is the algorithm. Again, I think it's fairly popular because it deals with networks without assuming that you know the number of clusters. More work is needed to understand it. What's the, did anybody guess where it comes from? Where the idea comes from? If you know Bayesian networks, and if you know approximate inference in Bayesian networks, then this will be very familiar, or this was very familiar to you. It's basically summing up the contribution of your neighbors and subtracting your own and passing it back to your neighbors. Okay. Yes?
It looks relatively iterative. Is it stable if the graph is changing? I'm not too quickly, obviously.
Again, only empirical results. Yes, apparently it is stable if the graph is changing, and apparently this changing the self-similarities gives you coarser or sort of larger clusters or smaller clusters, more granularity. Of course, the question is, how do you change a graph in a state? Like, what's a small change in a graph? And that's to be discussed. Yeah. OK, if there are no other questions, then I will stop here. Thank you.